Welcome everyone to the next ESGF webinar. We're fortunate today to get a presentation from Christian Pagé and Alessandro Spinuso. We're going to talk about some work that they've been doing with icclim. And with that, Christian, go ahead and take it away.
Thanks very much for this introduction. So first, we begin with the presentation on icclim. So I am Christian Pagé. I work at CERFACS in Toulouse in France. And this work has been done by several research engineers. And Abel Aoun was the latest research engineer to redo icclim from scratch 2 years ago. So icclim is what it is. It is a flexible tool to analyze climate simulations. So you'll see more about it in the next slides. So this has been funded by the ESGF project, so the European project on the infrastructure for climate modeling. So icclim is an acronym for Index Calculation for Climate. The aim is to implement the calculation of 61 standard indices. So for now there are 61, but we keep adding more. And those standard indices are defined by many communities that work with climate indices. For example, ECAD, TSCI, ETCCDI. So it's not important to know those acronyms, but it's just to tell you that those are defined within the community, those definitions. And so to be sure that everybody implements the same thing and that we can compare those climate indices. The climate indices can be categorized given the variable they are using to be calculated. For example, we have climate indices based on temperature. So heat and cold climate indices. We have wind indices, also those related to precipitation, so rain, snow, and drought, and also humidity based. And some climate indices are combining several input variables. Examples of climate indices, I have listed 3 there, but there are many more. So for example, we can have intra-period extreme temperature range. So it's called ETR in degrees Celsius. We can also calculate warm days. So it is defined as the days with mean temperature greater than the 90th percentile of daily mean temperature. And the acronym is TG90P. So this is standardized also. And summer days is one of the most simple ones. It's days with max temperature greater than 25 degrees C, called SU. So those are just a few examples so that you know what we are talking about. And so icclim is Python. So it's full Python right now. It has been developed at CERFACS since September 2013, so 10 years ago. It has been funded by 3 main European projects. It has always been developed with a generic and modular approach, so it can be reused, or some functions could be reused. And starting from the new version 5, it has been completely rewritten from scratch using the icclim functions. Icclim is another package to calculate climate indices, and we work together. And the goal is really to work in coordination with icclim. In the development of icclim, we also contributed to many basic functions in the icclim package. So those 2 packages are based on XArray and Dask. And one of the characteristics that is very important is that there's the implementation of the proper percentiles and indices calculations when we have overlap between the calculation and the reference period. So it's called the bootstrapping method. So all the available indices are available in read the docs with this link. So you will have the access to the presentation after the webinar. So documentation is there. We have Python API. The source code is on GitHub. Current version is 6.3.0 and 6.4.0 will be released very soon. This is the main function to access the climate indices calculations. It's icclim.index. This is the generic function. So it has a long list of input parameters. Most of them are optional. And it's just to show you a sample of the documentation. So the code, as I said, is available open source on GitHub with the latest standard in the coding has also been used. It's also available in Conda, in PyPy. Each time there's a release, there's a DOI on Zenodo available. And automated testing for each release cover more than 90% of the code. So it's a code that is pretty active. And here it's a one-liner just to show you how you could compute easily a climate index. For example, you launch Python, you do import icclim, and then you just compute summer days with icclim.su. So this is a specific function for this climate index only, and then the input file, the output file name, and that's it. So icclim will know which input variable it needs, and it will also use all the default options on the other parameters. So we try to follow as close as possible the FAIR principles. So FAIR is findable, accessible, interpretable, and reusable. So findable, why? Because it's open source. It's a license under the Apache 2 license. Try to follow OpenSSF principles. So those are some standards for open source software. Documentation is freely available on ReadTheDocs. There's dissemination. Now, so it's integrated in the Climate Foreign Pack and soon in the C3S. So a Copernicus service for climate data analysis. Accessible, so we have GitHub issues and pull requests that other people can use. The development is supported by CERFACS and projects. It's available on Pipe and Conda. Interoperable because the code is based on well-known libraries, XArray, icclim, NumPy. It supports the NetCDF, XArray dataset input formats, as well as ZAR. So it's quite flexible for input. And so the indices are from ECAD and CF convention standards. There's also some parsing of input data to try to assess the input parameters from the input data, so when it's not compliant to a CF. It's reusable because we have extra metadata when we write the output. So it's easy to integrate with the existing infrastructure, and it's very easy to write a small script. So this is another example. So using a list of files as input. This is a percentile-based climate index, so it's TX90P that I presented earlier. So we have a base period that is specified there. And this is one way to call icclim.index to calculate the output of this TX90P. So many new features have been introduced in version 5 with the completely because we completely rewrote the code. So we have chunking available. So this is more complex aspect of icclim, because if you use it in low memory environment, or if you have multiple core but with not large amount of memory per core, then you can optimize the chunk using the ZAR store. And this is one way to do that. So this has been introduced in version 5.1.0. Also, computing multiple indices at once. So we have some recipes there available in the documentation. So we have groups of climate indices that we can calculate together. For example, heat related group. So those are available also to ease to make it more easier for users. We also have one function per climate index. So this was introduced to be compatible with the Copernicus C3S service. So as I've shown earlier, we have icclim.su for summer days, but we have one function per climate index. So there's a sample to the right-hand side, so we can see TG, TN, TX, and so on. And all those are available in a specific function. The advantage for using those functions is that you don't have to specify the input variable, for example, and many parameters can be optional. In 5.3.0, custom season between exact dates were introduced. So this is mainly for applications, for example, in agriculture, where you can have specific seasons from mid-May to mid-September, for example, or other dates. So this is just one example to show that we can use slice mode to specify the season. So we calculate only for this season that begins. So this is a random example. So 19 July to 8 August. So we see that we can also write the date in different formats. So this is possible using Panda. So for those of you who know Panda, you can write those dates in plain language or as you wish, because it supports many different formats. So in icclim version 6, really a very important feature was introduced. Those are generic climate indices. So you can define your own climate index in an easier way than it was possible before. So I will explain that in the next slides. So before explaining those generic indices, also in 6.0, there has been some fix related to the spells, because when you calculate a climate index based on precipitation, for example, you can have climate indices with event-based climate index that could span 2 months. For example, we have precipitation here. So we see that we have 2 events with less than 1 millimeter per day. So if we want to compute CDD, so it's a consecutive dry day. So we count the number of days with less than 1 millimeter per day. So we could ask ourselves, CDD in February should be 3 days or 4, depending on how you compute those spells. So as agreed with the community, we count spells now length before resampling into monthly values. So CDD in February should be 4 here. So this is a change from version 5. So back to the generic indices. So we could ask ourselves, what is the difference between those 3 climate index? So SU, summer days, FD, frost days, and TX, 90p. So we have, for the first one, we have the number of days where TX is greater than 25, FD is TN less than 0, and TX is greater than the 90th percentile. So we have operator, variable, and threshold. So what we do here is that we can define a generic way to represent all those climate indices using those 3 specific features. So operator, variable, and threshold. So an example here of a generic climate index that you could define. So you could say, okay, summer days is nice, it's 25 degrees Celsius, but I'm living in Finland and 25 degrees is very rare. So summer days for us is more 20 degrees Celsius or warmer. So you could compute that if you want. So you can define your own climate index with the variable name is maximum temperature, so Tmax. We want to count the number of occurrences. So the index name would be the operator. And the threshold would be greater or equal than 20 degrees C. So we have those three features to have this generic climate index. And the metadata that is generated for the output is also using the standards as close as possible to CF. So we would have those metadata automatically generated from the definition of the generic climate index. So we could have others. So for example, R75P exists. It's a ECAD, so it's the precipitation, daily precipitation greater than the 75th percentile, whichever or equal. But we have two thresholds because we want to be greater than this percentile, but we also want to count only with the minimum value of 1 millimeter per day. And we have this reference period, so you can see also the dates in plain language or in numbers. And then you would specify the index like the second line. So you count occurrence. The variable name I want to input is precip, and the threshold defined as the first line. So we can also do CW. So it's where we have wet and warm days, and we can have multiple thresholds on multiple variables as input. So we have two input variables, two thresholds. And we could also define other climate index that we could be interested. For example, we can add wind. So we have precipitation, Tmax, and wind that are considered in this climate index. So we have a lot of many possibilities with many operators available. So those are all the list of operators available to calculate, to create new climate indices. And on the right-hand side, we have the standard indices that are using those operators. So for the first one, we don't have the full list because it's quite long, but we have also the other ones. So on the right-hand side, you see the documentation that will give you some information on all those operators. We also have those threshold. So threshold can be scalar, day of year percentiles, period percentiles, and so on. So we can have also per grid cell threshold. So this can be interesting if we have a threshold that is not the same in the specific part of the grid. We can also have sequence of scalars. So there are also some examples in the documentation. We have sample notebooks based on icclim to compute climate indices. So it's hosted on GitLab. So we have 5 notebooks. They will be updated soon because the user index 1, so the last one, is no longer relevant because we now have generic climate indices. And in those notebooks, you also have some tips on how to deal with pre-processing and especially post-processing the data to plot it in nice ways, and to also overcome some limitations in Matplotlib and Cartopy. So that's it for my presentation. And so the presentation will be available. So documentation is there, and feel free to try the code, install it, and also give us some feedback or ask questions. So thank you.
Thanks, Christian. Shall we switch now for Alessandro and take questions at the end?
Yeah, sure. I guess I'll share my screen now. All right. Can you see my screen?
Yes.
Yeah. And I'm gonna go in full screen mode.
Looks great.
Yeah. All right. So welcome everyone to this webinar. And yeah, so this presentation is given by myself, Alessandro Spinuso. I'm a researcher and project leader in the data technology department of KNMI. And so it goes over the new implementation of the Climate for Impact portal with the objective of enhance the use of climate research data and methods. It has been developed mostly at KNMI, of course, with the contribution of the expert that we have available, like Christian, that is also providing the icclim library, which basically we hook behind the scenes to allow our specific climate impact analysis. Climate for Impact is an online platform where we combine the capabilities of discovering climate data from the ESGF with the experimentation workspaces, with the particular design of having these workspaces offering a reproducible climate impact analysis. The project and the website and most of the development is basically financed by the Easiness research infrastructure. In this particular framework, we build tailored tooling and also infrastructure service and training, like, for instance, the one that we are just giving at the moment. And the aim of this project and the portal itself is to support research on predicting and mitigating climate change effect on the whole Earth ecosystem. I mentioned already that Climate for Impact is using data coming from the ESGF. I'm pretty sure that you guys are mostly aware of how ESGF is organized, or what the ESGF, the Earth System Grid Federation, entails. It is definitely a multinational effort for the management of climate environmental data. The reason why I'm putting these slides on is that I want to highlight the structure of the, let's say, a little bit of the organization of the ESGF, which is characterized by a federation of different nodes. And these different nodes, they host different capabilities. Like some nodes are providing data, they have also some computational functionalities that are made available to the users, and some are also hosting particular access control mechanism. And so it's a quite of a variety of different services, although they are tend to be offered according to some sort of standard in terms of the data access, and how I will show also what we would like to achieve is also some sort of level of standardization on the computational level. I mean, I'll show you how this is at least implemented within the initiative in Europe, and how it connects with the C4I. So I want to highlight also that there is work that has been done to improve the way that we identify users and we authorize users to access some of these particular services. So we have a new implementation for an authentication system, which is basically used by C4I in a very sort of pioneering and experimental way, but so far, I mean, we have quite a number of users registered already. So given this general background about the ESGF, so we wanted to comply with this general architecture by having that reflected within this user-based or user-facing service. So we have implemented within Climate for Impact 2 different profiles. We have a guest user, which is who is allowed for basic search and local data download, or you can become registered users and therefore get access to additional capabilities, like having workspaces for data analysis and also accessing subsetting services on the remote node of the federation where these are available. Soon to happen in some particular nodes, at least in Europe, is to open also this to Cordex data. So the registration procedure that we have put in place at the moment requires to send an email to the C4I at KNMI.nl, specifying basically your affiliation and motivation to become a registered user. We don't store any of the information within about the user within our KNMI, let's say, domain, but we need to this step just to provide the computational resources in a meaningful way. So, but all the identity is managed by the ESGF node, which is responsible to keep the ESGF login node, let's say, that is responsible to keep all the information about the identity of the particular user accessing the service. So this can be handled in single sign-on by using all the typical GitHub or ORCID or even the ESGF CEDA accounts. And basically, once the user is approved, then you can log into our system and access all of the capabilities via the single sign-on service provided at CEDA directly. Given this preview of how we manage and handle the user identity at the moment, so the portal itself is also organized depending on the different projects which are handled and managed within the ESGF Federation. So we directly have provide access to CMIP 6 and CMIP 5. Coming soon will be Cordex. The reason why it's coming soon, because the authorization system, it's really needed to get the Cordex data open and available to the community. And we want to make it, to do it right by using the new in development authorization system rather than relying on old implementation. So what we have implemented in this new version of the portal is basically we put in the forefront the variable which are more relevant for climate impact analysis. And so these variables are then also organized by different type of facets, characteristics, like we have the variable parameters, then we have the frequency, the experiment, the model, and members. So users, they can go through all these tabs and select basically what they find more relevant to their interest. At the same time, I mean, this variable that you see now, they are a subset, but they can be also extended by switching to an extended view, which gives the opportunity to go through the whole collection of possible facets which are available for that specific facet domain. So, and this was also something that was requested to make it more evident from one of the webinars that we gave in the past. So we are not limiting the scope, but we are just applying this layer in order to facilitate the choice for the particular use cases that we want to offer. The next option is that you can also narrow down the scope of your search on those nodes which are providing a particular capability. In this case, I mentioned already that some of the nodes are providing some computational capabilities. Particularly, we are looking at services offering subsetting functionalities in order to obtain data reduction. And we have in Europe already an implementation from 2 different data nodes of the Federation. So users, they can decide interactively to select only those nodes where the WPS, so the remote web processing services offering downscaling and subsetting is available. So that's very generic, and this is available to guest users, and the web service, the web processing services is available only for registered users, but nonetheless, for all users, it's always possible also to select the model based on some performance evaluation that we obtain by importing data from another service of the Easiness software architecture. So we provide users with the possibility to compare model performances based on the changes calculated on 2 variables, so temperature and precipitation. So based on their selection, they can see basically in a a graphical interface, how these models perform compared to the others, and also with indication about the bias that they have with respect to the ERA 5 dataset. So this is interactively available and should suggest more or less if the model that I'm looking at or that I'm about to ask data for it's fitting basically what I expect. Having done this possibility, then typically what happens according to the former and more, let's say, old school way of doing analysis on this type of data, we provide the opportunity to select information and data per file and to obtain what is called a metalink file that collects all the results of the user selection, which is coming from the search that has been obtained by the parameterization and options that I was showing before. And once the user has selected the data, they have the possibility then to download the descriptable format and basically download the data wherever they want. However, the thing that we have been mostly interested within the new implementation of Climate for Impact 2 is the possibility to provide actual workflows and workspaces where this analysis can be done directly on the cloud and in a sort of controlled environment. So what we provide for registered users and therefore validated accounts is the opportunity to have a full data staging and or let's say subsetting data within personal workspaces. So in both cases, we do offer very large storage within these online workspaces. However, because of the, let's say, occasional also high load on the ESGF nodes, we do limit each request, let's say, to a range of 3 GB. So this doesn't limit the extent of the total amount of data that you can put within your workspace at the moment, but let's say that each request should be tuned around a predefined size because otherwise we might end up in having workflows timing out. So it's not very good from the user point of view, from the user experience point of view. So this is a little bit controlled. So from the point of view of the subsetting functionality, we made it a little bit interactive in a way that once you can see that there are a number of parameters that should be set, we also offer the possibility to link to an external service which gives the opportunity to draw the typical bounding box in a way that you can clarify in a more interactive way how you get these parameters to configure the subsetting functionality. In both cases, the data is automatically collected and basically staged within a cloud infrastructure where you have access, in this particular case, to notebooks that are already providing you with all the environment where icclim would perform at its best. So you will get access to Panda, all the visualization modules that you might need. And this is basically assembled for you on the fly. So a little bit of the background of why we and how we did this. So Swirl is the virtual research environment API that we use behind the scenes of Climate for Impact. Is a generic environment that manages data-driven and collaborative workspaces. It can associate with the data different type of services like notebooks, workflows, and in some projects we also use visualization tools. And it is basically an independent component that runs on Kubernetes cluster. It runs happily, in this case for Climate for Impact, on Amazon as well, but we have also other type of implementation. So we have this implementation done, let's say, as a technical realization of a more generic framework, which we call a workspace orchestration framework that evolves around different concepts like sessions, workflow, service, and service pools. The idea is that we can create on-demand data spaces based on a number of data sets that can be regularly up to date. And then these data spaces can be associated with different service pools where a group of users, they can basically collaborate on a shared objective, a shared research target. So within the service pool, each user will get access to a number of services, as I said, notebooks or visualization tools, and they will share, they will have access to the same data sources, but they will also share the same working volume in a way that the results of the work that they are pursuing is basically visible within the confined domain of the pool. And this is all managed by the API, which provide a high-level interface where all of this type of organization is handled. What I should mention is since, of course, the notebooks are the, let's say, the preferred at the moment tool that are very popular among the different users, we have decided also to implement within the notebook itself reproducibility controls. So as I said, the virtualization environment runs workflows behind the scenes to update and collect this data or subset them, depending on the type of workflow that you have selected to use. And within the Jupyter environment, we have created an extension that allows you to monitor the execution of these workflows and also to log into your GitHub account in a way to allow users to create snapshots of their progress. So at some point, if you want to store your, let's say, notebooks and the intermediate results to be shared with other people, even outside from the domain of Climate for Impact, you can automatically create a binder repositories on GitHub. So Swivel does it for the users automatically. And these repositories are then basically completely independent in all their aspects, but the data. We don't store the data within GitHub, of course, but we keep the pointers to the data space that is still managed by the Climate for Impact portal. But basically, who runs the binder in a My Binder environment, they will be capable of fetching the same data again. So it's very important to emphasize that it's the same data. It's not the data that have been version updated in the meanwhile. So this is really built with the reproducibility in mind, so that we actually know what the user is reproducing in a different environment. So this is all handled because we do an automatic provenance management behind the scenes, and this provenance is also used to show to the user a number of actions that have been performed, and also to roll back those actions. Workflows that have been executed in the data space can be rolled back to make sure that we go back to the situation that we had in a previous stage. And we have also the opportunity to access the provenance of these workflows in an interoperable way. So we use the W3C prov format to manage the provenance behind collected by the system and generated by the system. And even if you have updated your notebook environment with some software libraries, we have the possibility to give you the option to roll back those installation and give and respawn an environment that was working for you until let's say a few days ago. But then, I mean, by experience, we all know that when we start playing with Python modules, so we can get immediately into some sort of conflicts, and by trying to fixing them, we just make it worse. So we decided to give the option to recreate situation that were working in the past. The importance of having this reproducible and fair management of provenance and therefore traceability is also useful for us to collect information about computational KPIs. So these are just examples about statistics that we collect from the notebook that have been generated, the data sessions, the rate of success of those particular notebooks, workflows that have been executed, and also the data files that have been fetched, and also in terms of unique data files. So we can identify which are the files which have been more popularly requested by the users of C4I. And at the moment, we do have more than, actually much more at the moment than 100 users registered via the new also experimental ESGF single sign-on infrastructure. So, I mean, this presentation is, let's say, a bit, I wanted to give a user perspective, but also a little bit of the technical side for the technology used behind the scenes, because I think that this was also one of the target audience that we have within this type of webinars. And okay, the work which is going on is therefore covering technical aspects, but also user and usability aspects at the same time, since we do want to open Cortex data entirely via this platform as well. It's constantly requested by each user that is asking an account. So very often they do want to have access to Cortex within this environment. So I hope that we manage to make that happen in the next future. We are doing an experiment within CEDA at the moment, which is giving some positive results. The WPS itself, now we have only 2 nodes in Europe, which are who are supporting the implementation of the subsetting. We really hope that this federated access to computational functionalities can scale to other nodes, even across Europe, beyond Europe. And as Christian was mentioning, we need more examples. icclim is powerful. It's even more powerful if you give examples to users that can be run within such an environment, coupled with scientific guidance, and eventually really, I mean, using all of this to empower more collaboration on remote infrastructures rather than still promoting access and local download of the data. So if we can allow this to happen in a more controlled but still free environment, we believe that we can really provide a service to the community. And thank you.